Welcome to the Thomistic Institute podcast. Our mission is to promote the Catholic intellectual tradition in the university, the church, and the wider public square. The lectures on this podcast are organized by university students at Thomistic Institute chapters around the world. To learn more and to attend these events, visit us at thomisticinstitute.org.
This morning I have the privilege of talking to you about CRISPR. We're going to talk about the science of CRISPR. I'm not quite sure what your background is, so I want to make sure that all of us here have a basic foundation on the science of CRISPR. And then we're going to be talking about ethics. Now, it's interesting. So for many years, I did science here in the United States. But last year, after COVID, I got involved in COVID management in my homeland in the Philippines. In 2020, I went home for spring break to give a talk at the University of Santo Tomas and to visit my mother for what was supposed to be a 5-day trip. But I landed there on March 10th. And on March 15th, the world locked down. So it was a 100-day lockdown in the Philippines. You could not leave your gate, except for once a week, you had to get a barangay quarantine pass, and you'd go to the supermarket for a couple of hours. And so I ended up teaching my classes on Zoom. But what was striking, too, is that I had nothing else to do. And so MIT at that point had developed, scientists here at MIT had developed a model for the pandemic spread. And so what ended up happening is I ended up just downloading that and tweaking it here and there. And we used it for pandemic management in Manila. And then I ended up just getting sucked into the entire pandemic management process. And after 2.5 years, first of all, I just learned so much about human beings and the struggle to make vaccines. And so what ended up happening is in the course of the pandemic, I decided to pivot my research from cancer biology to vaccines. So we are developing a yeast oral-based vaccine for COVID-19 and for African swine fever, which are two of the pressing pandemic challenges in the Philippines. We're basically taking yeast, and I learned how to do yeast work here some 25 years ago. That's all I did, yeast. So what we're doing now is we genetically engineered yeast to secrete the SARS-CoV-2 spike protein. We put it into mice. It induces an immune response. So I went home last year, got transferred home, moved my laboratory home to try to push that further into clinical trials. I didn't realize that doing science in the Philippines is so different from doing science. There are particular challenges of doing science in a developing country. We worry about water. So my students will text me and they'll say, look, we ran out of water. There's just no water. We turn on the faucet, there's no water. So I go, okay, let's go to the supermarket. Let's buy several gallons worth of water, bring it back. So off they go. And so what's happened in the last year, I'm setting up my laboratory there. Procurement is particularly difficult. So if you want to buy something, it costs 4 times as much. If you bought it here, it would take 8 months to a year to get it there. So what ends up happening now is I come back to the U.S. every 4 months or so. There's a wedding for me to do, a baptism I have to do. Then I bring 2 suitcases and I go on eBay. We buy, I'm flying home tomorrow with multi-channel pipetters. We have a UV spec that I'm trying to figure out how to put it in a box. And then I have NEB reagents that we bought, and I have ice. We just pack it in the ice and get home, and my students will be waiting when I get off the plane. Unload, go to sleep. And it's fascinating to do science that way. It's also really crazy, but it's wonderful. It's wonderful to do science. And so we're going to be talking about first world problems here. We're going to talk about the science and ethics of CRISPR. I got home, I brought CRISPR home. I didn't realize I was the only one who had CRISPR. So now the government is trying to figure out what I can do and what I can't do in the country because they don't have any policies for CRISPR. So again, it's so fascinating to be part of trying to build up the infrastructure of science in my homeland. And I have 26 students now that I'm training. You know, I had the privilege of an MIT education, and so I'm trying to give some of that to them. And we have journal clubs, and I teach them how to read papers the way I learned in course 7. And it's just really, really cool to be able to do technology transfer to the Filipinos. So what's going to happen today is I'm going to divide up my talk into 3 bits. The first and the third are the really big bits, but we have one important distinction that I would like to discuss. So we're going to talk about the science. We're going to deal with the distinction of therapeutic and non-therapeutic, because that plays a large role in the ethics of this question. And then we're going to talk about the ethics, basically an ethical framework in which you can think about doing this kind of work, or pretty much any work that involves human beings. So we're going to start with the science of CRISPR, and I'm going to have to begin with the very basics. So for those of you who are not course 7 and not course, I understand there's a 6, 7 now. There's combinations of courses that I didn't know of before. So this is a genome. So the genome consists of all the genetic information in an organism. And so this is our genome. If you look at the nuclear genome, there's 46 chromosomes, 23 from mom, 23 from dad. And we inherit that from both parents. But a lot of people don't realize we also have a mitochondrial genome. And that's a genome you inherit only from your mom. And what's really striking is, if you heard of mitochondrial Eve, that's the discovery some decades ago that we are all descended from a single woman, because all our mitochondrial genomes, every single human being on this planet, is related to that original source, and we can follow it as it is inherited down over the millennia. But I have to point out, this does not mean she was the only woman who lived at that time. And there are theological repercussions for that. So if you take one of these chromosomes and you spread them out, you get the iconic double helix, the DNA molecule. And one of the, every time I give this talk, I always point out that it is said that we live in the century of biology. So chemistry was the 19th century, physics the 20th century, and this is the 21st century. This is now where science is really interrogating the structure and function of life, and really we have the tools today to actually manipulate life in a way we've never had before. Now, one of the pressing questions and challenges over the next century is really trying to uncover and figure out how a genome, the size, if I stretched out your genome, it's about 7 feet. And imagine a 7-foot long piece of spaghetti, and you're going to go ahead and roll that up, and you're going to put it into a single cell. And the cell, the largest cell of the human body, is the period at the end of a Times New Roman font 12 sentence. And so you're going to take the 7 foot, and you're going to put it in such a way that you can identify and look for all the genes at the appropriate time and at the appropriate location. And so we really don't know the Dewey Decimal System for this incredible library. And as you can see, this image is supposed to try to convey the sophistication for how this DNA is structured. It's not just spaghetti. It's spaghetti that's rolled and compacted in very, very precise ways. And the epigenome is basically what you're looking at right now. Now, if you're looking for the DNA double helix, it's usually indicated in this way. So DNA is made up of repeating patterns of 4 molecules, nucleotides, and they're abbreviated GATC. And so what you can see is you have something like this. This is actually the open reading frame, the sequence of the gene for yeast Bax inhibitor, which is the gene that my students had been working on in Providence College for a decade, where we've moved, because we've pivoted my research, this is kind of in the back burner at the moment, but you can imagine that your genome is about 3 billion of these letters. So now you have the analogy where your genome can be equated to text. And since you have 46 chromosomes, you can imagine your genome is like an encyclopedia of 46 volumes. And as you're going to see in a minute, CRISPR allows us to edit those volumes. So we're now moving to CRISPR. This is what it's clustered, spelling mistake, clustered regularly, interspaced short palindromic repeats. We really don't need to know that. They named this not knowing what it would eventually do. It's really the bacterial immune system. If you want to talk about where did CRISPR come from, it's a bacterial immune system that we have used and modified so that it's now a molecular editing machine. So CRISPR is made up of 2 components. There's a protein component, that's the blob, the green blob, the Cas9. And then you have an RNA component. And the RNA component is information. And what this information does is this information targets that green blob. So you can tell the machine where to go in the genome by simply altering that guide RNA. So at this point, in principle, we could take volume 8 out of that encyclopedia, turn it to page 222, the second column, the 4th sentence from the top, the third letter from the right, and then we can go ahead and change that letter from E to an A. That's the kind of precision that this technology offers us. And so in terms of what it does, you have to imagine that all this machine does is it cuts DNA. But it cuts DNA in very specific locations that are determined by that guide RNA. So this is really, in very simplistic ways, what happens. So here's your target DNA, and the guide RNA will bring the blob, the Cas9, which think of it as like a pair of scissors, and it cuts the DNA. And since the DNA is a double strand, it will cut the DNA twice to generate what is called a double strand break. Now, double strand breaks are a major no-no for human cells, for any cells, because they trigger all sorts of molecular processes that often lead to cancer. So what ends up happening is the cell is going to attempt to fix that double strand break. So on the left-hand side, what you see here is the cell will attempt to fix that double strand break. And in doing so, it's going to snip back. So it's going to trim that break. And in doing so, it removes some of the information that is indicated in that sequence. And so when the DNA is religated, when it is glued together, what ends up happening is you lose information and the gene is disrupted, the gene is destroyed. So this is what would normally happen if you just simply introduce CRISPR into a human cell. But what we were able to do is we are able to do gene editing. So what instead of simply introducing the guide RNA and the scissors, you can also introduce a DNA sequence that the cell will use to repair the break. And in repairing that break, the cell will replace the native information, the information that was there, with the information that you provided. And this way, you see, you now are able to edit any piece of DNA anywhere, anytime. Now, the Nobel Prize in 2020 was given to two scientists, Emmanuelle Charpentier and Jennifer Doudna. She's in Paris and she's at Berkeley. And for the reason that they were the first to show that the CRISPR machine could be used as an editor. So CRISPR, as I alluded to, was discovered as the defense mechanism of the bacterial cell, but they were the ones that were able to show that you can now take this and do something new with it and do genetic engineering, genome editing, basically. So I'm just going to highlight a couple of things that have been done so far so you get a sense of the breadth of the revolution in biology that is ongoing, as well as the ethical questions that arise because of what we're able to do now. So this is one of the earliest experiments. So here you have a mouse. The mouse is carrying a mutation in its gene. Because of that, its liver is not functioning properly, and it has hereditary tyrosinemia. And humans actually have an analogous disease. So what you do is you take the CRISPR machine and you introduce it into the liver. Some of the cells in that liver are going to be edited, and then some of the cells in the liver are able to make what was missing. And so what you do is you end up getting a repaired liver. And so in principle, this can be done with humans as well. Now, this is gene drives. Most people don't think of this, but this is actually an incredible area of ethical debate. So on the left-hand side, imagine a population of mosquitoes. On the left-hand side, you have a mutation indicated by the red, in this case, fly. And the normal Mendelian genetics will dictate that over the course of several generations, that mutation is going to go down a certain pedigree. What we can do is we can use CRISPR. I'm not going to go into the actual technology, but what we can do is we can use CRISPR to force inheritance. And so what ends up happening is now you have a scenario where after several generations, pretty much the entire population of that target of the organism now inherit the gene. Now what you can do is you make this gene a sterilizing gene. This is a gene that makes babies sick, or it's a gene that makes, progeny ill. So you can eradicate, in principle, an entire population of animals, organisms, and there's a debate over whether or not we should do this with one species of mosquito. Now, just to give you context, there are about 3,000 species of mosquito that are extant. And so the question is, can we get rid of one of them, Aedes aegypti, which is a vector? It's an insect that basically carries and transmits a whole bunch of human diseases. The question is, should we eradicate that particular species of insect? Now, you may go, well, that's going to be messy. We've already done it, right? So we got rid of smallpox. We got rid of one of the species of virus, and no one has complained that, it's a mess. Now, one of the things that we have to keep in mind is that smallpox, being a virus, was very, very specific for us. A mosquito is part of an ecosystem. And so the concern here is you remove one of the pieces of the puzzle and the whole the whole castle collapses because one of the pieces is gone. So there are actually ongoing experiments to do this. They're doing it on an island in the Caribbean. Now, being home in the Philippines now for a year and a half, I've become very, very sensitive to how many white, first world, northern, very tricky experiments end up in the third world. Why not just do it on a remote island in the Michigan? Well, there'll be problems there, right? So we move it to the Philippines or we move it to the Caribbean. We can't do it in the States. I've just become sensitive to that. You just don't realize that. And you go home and you see the poor, and what you see how biotech companies fly to the Philippines, they offer an exorbitant amount of money for Filipinos to be part of a clinical trial. And in many ways, it's hard for them to say no. And I think there's an exploitative dimension to that we really have to think about. Yes, it benefits the entire global population. But like I said, why is it that the risk has to be borne primarily by the poor? Okay, so this is Anopheles gambiae mosquito. So this has been done. Gene drives. It's also been done in mice and rats. And, there's talk about let's get rid of all the rats in the New York subway, and we'll do it this way because you see, it's organic. You don't have to use these nasty pesticides. This is an organic way of controlling pest population. It's very fascinating how you describe it and how you talk about it and how you frame it. But I've heard people just say that. It's like, it's organic. And I know people go, whoa, that's really cool. And then you don't realize the wider repercussions of that. So there are technologies in place to try to make reversible CRISPR, inhibitors of CRISPR. I have no time to go into all that technology, but the idea here is, can we set up a system where if we mess up, we can undo what we did? Now, moving now to humans. So the first distinction I'm going to talk about is the distinction between in vivo and ex vivo editing. So in vivo editing, you take the editing machine and you directly introduce it into the patient. And this is usually done with certain viruses that have been customized so that it targets the virus to a particular cell, a particular organ in the human body. Then we have ex vivo editing. Here what you do is you take stem cells out of the body and then you play with them in your lab. You can check them in your lab. This is the added advantage. And then you get the corrected stem cells and you put them back into the patient. And hopefully you know exactly what went back into the patient. See, part of the challenge with the in vivo is that you simply are introducing the engineering machine directly into the human patient. You have no sense of where it went, what it did. You have a hope that it's doing what it has to do. So the classic example for this is sickle cell. So what you do is you take the hematopoietic stem cell, the pluripotent stem cell, which is the stem cell you get from bone marrow. There's a particular mutation, it's GTG. In your lab, you use CRISPR, you change it to GAG. You try to make sure that nothing else was changed. And then you take it and you put it back into your patient. And there are papers that describe the success of this technology. So in 2019, you already have human hematopoietic stem cells, therapeutic gene editing. And then in 2022, you actually have patients who are benefiting from CRISPR-based gene therapy, which is why last month, so in October 2023, this is from the New York Times, there's a possibility that the FDA will approve sickle cell anemia CRISPR therapy. It'll be the first CRISPR therapy that's approved for public use. Pretty much, I think, anywhere, to the best of my knowledge, anywhere. Now, what's also being done actually here in Cambridge, so this is Editas Medicine, which is down the street, right across from the Hotel Sonesta, the Sonesta Hotel. And one of the things that's really striking here is this is an inherited blindness. So this is Leber congenital amaurosis, LCA. Now, I was down there some years ago before COVID and just talking to the scientists there, and I learned so many things about blindness. You know, you and I are so used to be able to see 20/20, and then we have all the corrective devices if necessary. When you're talking to someone who's facing a future of darkness, what you discover is they don't really want 20/20. I mean, ideally they get 20/20 vision, but that's actually not the goal. The goal is they want enough to see so they can walk an obstacle course. And it makes, it's a black and white quality of life. Just talking to them, quality of life. If you can see an obstacle course, it makes a tremendous difference to the way that you can get around. If you cannot, then it's very difficult for you to leave your house. And so this is a technology where there is a genetic mutation. It's a splicing mutation. I don't have to go into the details for that. What happens is on the left-hand side, because of that mutation that you inherited from one of your parents, the retinal cells, the cells that will receive light in the back of your eye, over time, they basically commit suicide and they die because there's a photoreceptor defect. And the idea here is that the CRISPR will fix that splicing defect so you get normal protein, normal product, and the normal product will sustain life of that retinal cell. Now, what's an added advantage for this, of course, is that the eye is easily accessible. All you have to do is inject the CRISPR machine directly into the eye. I know it's kind of gross, but people do it. And we do it routinely. So LCA, what's interesting is that this is in March 2021. So there's clinical trials of this. What's fascinating, I haven't seen the paper. If you read the news articles from the reports, the public reports, it helps some but not all. And no one's quite sure why CRISPR can help some people but not all, but it's a work in progress. Now, Intellia is another company here in Cambridge, and they also use CRISPR. In this case, they gave the patients one shot of the CRISPR machine that was directed to a gene KLKB1, and it was able to ameliorate some of the disease symptoms, the phenotype associated with the original genetic defect. So what you're seeing here is you've got in vivo, we have ex vivo with sickle cell, and you already have progress with in vivo gene editing. Now, the second distinction I need to make is the distinction between CRISPRing, editing, cells of what are called present persons. So we are all present persons. And then there are future persons. These are people who are not yet. So these are kids. These are kids who have not yet been conceived. So on the left side, you have what is called somatic cell gene therapy, or gene editing. So this is where somatic cells are all the cells in your body other than your gametes, sperm and egg. So the genetic change will affect you, but it will not affect your children. That's what somatic cell. Anything that affects your children is germline gene editing. This is where I go in there, I change your sperm, I change your egg, and basically what ends up happening is the resultant human being that is generated is now mutated throughout his or her body. And now what you can see then is their offspring will also carry the mutation. This is why it goes from generation to generation. This is future persons. And the ethics between these two, as we will see later, are different. So in terms of human embryo editing, so this is the work from Shukrat Matalipov, who's over at Oregon. And so in August 2017, he published this article in Nature where he reported doing genetic engineering with human embryos. Now, I'm not going to get into the details, but this paper was received critically. The way that the experiment was designed, it's really hard to know if what they said happened really happened. Okay, there are some tweaks that there are possible interpretations of the data that would lead you to believe that CRISPR didn't happen. So it was not as clean cut as you may want it. Now, this is November 2018. So a year later, at the second International Summit of Human Genome Editing, this is He Jiankui. He's a Chinese scientist who reported that he had genetically engineered two girls, twin girls, Lulu and Nana. This is not their picture. We don't know where they are. Hopefully, we will never find out, because if we found out, they would become subject to experimental. They would become guinea pigs, basically. But his work was heavily criticized. He was actually imprisoned for some time. But he's out of prison now, and the last I've heard, he's back working. We're not quite sure what he's doing, but he's back working in a lab. Now, so this is the work, and he had convinced. So what he had done, just to give you context, is he had gone to families, poor Chinese families, where the dad was HIV positive, and then convinced them to give him permission to genetically engineer their babies using CRISPR so their kids would be resistant to HIV. The problem is that it's unsafe. There was no way for knowing whether or not the genetic engineering was precise enough, because one of the difficulties is you've got 46 volumes. Yes, you're going to try to go for page 46 in volume 3, but you have to be able to make sure that editing machine is absolutely spot on. Otherwise, you'll go around and start nicking and causing changes elsewhere, which would then lead to probably cancer. Now, in June 2020, there was a series of papers that started coming out that revealed that CRISPR, as we understand it today, causes great havoc in human embryos. So here in June 2020, in a paper in Nature, what they discovered is that the chromosomes were rearranged. Okay, this is not a good thing. And then in 2023, again from Schukraut's lab, there were large chunks of DNA missing if you try to CRISPR these human embryos. So the idea here is there's evidence that CRISPR, as we have it today, as we understand it today, is still not precise enough. We don't have the kind of control that you would want to have if you wanted to deploy it for working with embryos. And we'll talk about what that would mean later. So earlier this year, at the third International Summit of Human Genome Editing, there was a consensus statement amongst all the scientists present, the ethicists there, that it's still too risky and we shouldn't go there. Okay, it was just not going to work. Now, we're going to just move to the CRISPR-inspired technologies, a couple of slides on that. So this is base editing, and I believe David is here. I think he's here at MIT. I think this is an MIT lab. So this is base editing. So if you remember, what the original CRISPR does is it cuts two strands of the DNA. So what happens here is it actually cuts only one strand. So that decreases the probability of error. And what it does too is it replaces a single base. Okay. So what you do is, in this case, it just changes the single base. Single letter gets changed without a double strand break, a double cut. And so that's base editing, and the CRISPR prime editing is where you only make a single cut. So these are different versions of CRISPR, but they have been genetically engineered in the lab to do different things in the hope that these new technologies will avoid the pitfalls associated with the original version. But it's already these technologies are already being used. So base editing, this last year, December 2022. This is a young girl in the United Kingdom, and she had acute lymphocytic leukemia, and they used CAR T technology that had been CRISPR'd to basically put her cancer into remission. And this is a paper, March 2023, again, using its T cells. So T cells are the soldiers of your body. And so the idea here is that we could genetically tweak these soldiers. We could make them more robust, more resilient, and maybe even more targeted. So you can see where the technology is going. And this is, in this case, this is severe combined immunodeficiency. This is a bubble boy syndrome. So individuals who have severe combined immunodeficiency do not have any soldiers, and so they can't go out because they'll die from normal infections. Using adenine base editing, that technology, they were able to generate T cells back into these patients. So now we're moving, that's kind of just like an overview of the science. What I'd like to do now is just move to one distinction that's really important. So this is the distinction between therapy and enhancement. In this debate over whether or not we should use CRISPR at any gene editing tools. There are several other classes of tools. A lot of people will say therapy, okay, enhancement, not okay. So it's usually defined this way. So therapy is to return the patient to the species norm. That's good. Enhancement is to move the patient beyond the species norm. And a lot of people say this is playing God, this is evil. Okay. Now, I challenge this distinction because I don't believe it's a robust one because of the following scenario. So if I ask the question, what should target LDL levels be for patients who are at risk for cardiovascular disease? So LDL is bad cholesterol, and you want to control that at a certain age. They start doing lab tests, and every single year you're going to have to check your LDL levels. Now, this is a question. What should they be? Now, to give you a sense of the possibilities, so the average LDL level among U.S. adults is 100 milligrams per deciliter, and the normal range is 90 to 130. Okay, so again, remember, you're a doctor, you're a cardiologist, and you got a patient in front of you. You're gonna try to figure out, he's got high LDL levels. You're gonna try to push it down. Where do you stop? And this is the species norm. Now, what's really interesting is that standard of care in the United States, pretty much all over the world, is the lower the better. So optimal is you go down below 100. Now, to give you a sense of what sort of lower threshold you have, hunter-gatherer tribes, 70 milligrams per deciliter, gorillas, bonobos, chimps, 30 to 50 milligrams per deciliter. And we actually have one human patient that we've already discovered so far. He's a mutation in the PCSK9 gene. We don't have to go into what that does, but he's at 15 milligrams per deciliter, and he is just fine. So now you go, where? So where are you going to go, right? So you're going to do therapy, or you're going to do enhancement. Now, again, if you look at the target levels, if you're just going to focus on therapy, then maybe 70 to 130, because hunter-gatherers 70, monkeys 30. Okay, we don't want to be monkeys, so we're going to stick to hunter-gatherers, right? But actually, that's not the current standard of care. The standard of care is you go drop as much as possible, especially since this guy, 15, that means it's healthy to go 15. Let's just push it down. So if you see that, the studies show that the lower the LDL levels, the better. So everyone's goal is to go as low as possible. We're actually, if you look at the difference between therapy and enhancement, there's millions of enhanced human beings running around. Pharmacologically, not genetically. We have not genetically engineered them, but we've pharmacologically altered them using statins for the most part, in order to shove their levels down. And so and no one has complained. No one has said that this is bad. No one has said this enhancement should be ruled out because it's immoral. And it suggests, and so we are okay with lowering LDL levels even below the species norm in order to protect human health. So I've challenged the therapy enhancement distinction, and I've argued that there are therapeutic enhancements that actually promote the good of human health, and those are good. And so I've proposed that the distinction should not be between therapy and enhancement, but therapy versus non-therapy. And so this is the definition I propose. Therapeutic interventions seek to improve the health of the individual, and non-therapeutic interventions seek to improve the opportunity of the individual. Why do you want to do that? Probably because it makes you taller, smarter, more pretty, But the idea is it enhances your opportunities in society. And so this is really how I've distinguished the two. It's not about species norm. It's about why you're doing what you're doing. So now we move to the ethics. This is the last part. And I'm going to focus here. Ethics is controversial in the first world. It's not in the third world because everyone is basically trying to survive. I realize that debate is a privilege of wealth in an incredible way. When we were talking about vaccination, we have 100% vaccination in the Philippines. I don't know what it is in the United States. I don't think it came close to 100%. It became 100% because people were just like, no work, no pay. So they wanted to work. So they got the shot. And they also realized they had to protect each other, especially the poor. So it was just a very different mentality. I've come to appreciate how radically individualistic our worldview is in the first world, especially here in the United States. And going home to the Philippines now after 18 months, you see that the communitarian feel to it is just so incredibly different. Being a professor is so different. So at Providence College, it's a story I tell now. You know, we have advising for majors. When my students come, I go, what do you want to major in? I'm not sure. I want to be happy. I like reading, but I don't like writing. I mean, it becomes an incredible source of great angst. I mean, there's self-reflection. I have to be authentic. I don't even know what that means. You know, I'm an adult. I don't know what that means. But my 18-year-olds and 19-year-olds, they're all trying to be authentic, and I don't know what that means. I go home to the Philippines, my first advising meeting. They're all coming. Okay, freshman. Okay, what are you going to major in? I have to go talk to my parents. I'll let you know tomorrow. There was just no angst. It was not about whether I'm going to be happy or not. It was about my parents know me. So this is the view. They know me better than I do. They know I'm good in math. They know. So, and I have to contribute to the family. It's a completely different mindset. So in terms of anxiety, it simplifies life. Because you don't have to stress out about some of the things that my students here were so anxious about. I mean, even picking courses was so difficult because they had to figure out if this course would fit in with the path ahead. And I just said, look, I majored in engineering. Look what I'm doing now. I mean, the path ahead is unknown. And I just say, you know, just learn how to read, to write, to think, and to live with other people kindly. Right? So again, I like a little anecdote. I flew here to the US a couple of weeks ago, and I got on a plane from San Francisco to DC on my way to Providence. And I got on a plane. I had just got off the plane from Asia, and the pilot gets on and goes, ladies and gentlemen, we are in a 777. There are 400 of us on this plane. The flight is 4.5 hours to Dulles. Let us be nice to each other. Let us try not to fight. There's no need for yelling. I'm like, where am I? In the Philippines, you don't have this in the PA of the plane. You know, it's like, buckle your seatbelts, unbuckle your seatbelt. Here, it's like, let's be nice. It's like, you know, we're playing in the sandbox now. And then when we landed, he was like, thank you for being nice. We had no incidents on the plane. I was just, whoa, it's just crazy. It's crazy. I mean, like, that we have to do this now. And then you realize people are just really, really anxious and very angry. There's a lot of rage. You put them all together and you put basic economy and you put in the back there with the smaller seats, and then things get triggered, right? It's very, again, I come to appreciate so many things differently. All right, so for the ethics, I'm going to focus on this key concept, human dignity, not only because I'm coming out of a deeply the classical Western philosophical ethical tradition has roots in Socrates, Aristotle, and Plato, but I'm also a Christian. And so you'll see that it all kind of ties in together. When we bring up human dignity, what is so striking, I was in Germany last week giving a talk on this because their opening sentence, paragraph of their fundamental constitution, the Grundgesetz, appeals to human dignity as the foundation of German society. The Constitution was formulated in 1946, so you can imagine it was a response to the Nazi Holocaust. But now you go, what is it? Right? Then what is it? And we're going to spend a little time on what is it. I'm going to propose that it's really an answer to this question, how much are you worth? Now, it's interesting when you ask an audience, how much are you worth? Well, what is your price? Now, what's interesting is that I will ask, iPhone 13 Pro, like how much is it worth? And you may not realize this, but there are actually two values associated. There's the intrinsic value. This is the teardown cost. So if you were Huawei and you wanted to figure out how much it costs to produce this i13, you just buy one and you tear it down, figure out how much it comes together. The approximate $570 and the original, we're up to 15 now, so this you can get a 13 much lower than that, but the original suggested retail price was $1,000. And so that's the significant markup for Apple. So what you're going to see is that faith-based traditions, especially traditions that come all the way back, again, the Western classical tradition, will claim that human persons too have intrinsic and extrinsic worth, okay, that we have both. So the intrinsic dignity is the inherent worth. You are priceless. And We do this in bioethics. So I point out when I was in Germany last week, if you are talking, if you've got a 22-year-old German college student and you've got the chancellor of Germany and they both need a heart, okay, when they both need a heart, and there's only one heart to be transplanted, we do not automatically give it to the chancellor. The same thing happens here. If we did that, we would base all our discernment on extrinsic dignity. So extrinsic dignity is the social worth of the human person. It's a salary and net worth. For most students here, it's still 0 or negative, right? Because you have debt. But for the adults here, right, you get a salary net worth over the course of your life. Hopefully, your extrinsic dignity goes up. And then if you're a celebrity, if you're Taylor Swift, or if you are a president, you have office, your extrinsic dignity goes up. So you notice there's 2 accounts of dignity. But we, in bioethics, even here in the United States, we say it doesn't matter if you're a president or if you're just a housewife, a mom. What we're looking for when you're trying to give you a heart is who's the sickest. That's actually how it goes. You have scores associated with how advanced your illness is, because we believe inherently that we're radically equal. You understand there's this equality of human beings, and the equality rests on this intrinsic dignity claim. The reason why we're all equal is because we're all priceless regardless of how much we're worth. Now, being in Asia, especially with my colleagues who are coming from China, this does not make sense. I have Chinese philosophers, friends, colleagues, who will tell you, no, men and women are not equal. It's the most striking. When you go out of the West and you meet another culture, like, no, they're not equal. Men are worth more. They're more powerful. They earn more money. They can beat up women. I've heard that, right? So you see, it's a very interesting claim. Now, it's also striking because I say, no, all human beings are the same. And I've had one professor, no, that's not true. Why? Because you allow abortion. And I said, what do you mean? And when you allow abortion, you basically are saying that one class of human beings, pregnant mothers, get to decide whether or not other than a class of human beings, fetal human beings have worth or not. If she decides they're worthwhile, she'll carry them to term. If she doesn't decide that they're worthwhile, she will terminate the pregnancy. It's a very different way of looking at the debate over abortion, which of course is incredibly controversial right now, right? But they said if you allow abortion in your society, then you cannot believe in the intrinsic equality of all human beings. And I said, and then now you have women there, and they go, it's born human beings. And they go, well, ooh. They'll go, and then it gets scary. So the government decides, the state decides, the voting decides when there is intrinsic value. Then you see, it becomes really, really messy. But it's a perspective we don't really appreciate here. Now, notice if you have intrinsic dignity, the worth of the human person is simply because he or she is human. Okay, human. It is not earned, not acknowledged, not recognized, and it's absolute. This is why you can't have half human dignity, because intrinsic dignity, because you don't have half human being. Now, so there's no such thing as partial. Now you notice it cannot increase or decrease. It's like the tear down cost of that iPhone. Once that iPhone 13 is put together, for the course of its entire life, from conception until death, if you see the analogy, it is worth $570. That value doesn't go up, doesn't go down. You cannot lose that dignity. So in the debates over euthanasia, the argument is primarily centered upon extrinsic dignity. Now you're going to see that from a theological perspective, intrinsic dignity is grounded in the claim that human beings are made in the image and likeness of God. So this is a theological claim. Of course, in a secular society, in a pluralistic society, this does not have cachet. Now, in the Western classical tradition, the philosophical tradition, the intrinsic dignity claim is based upon this conclusion that we are partially spirit, and spirit is much more valuable than matter. Okay, and this has the nature of the way we think, the focus of abstraction. This is being challenged today by AI. The question is whether or not you and I think in algorithms, and there's a lot of debate about that. And that's another time, another talk. But the idea here is that you have philosophical, non-religious foundations for this notion of intrinsic dignity. And so an ethics of dignity is grounded in the claim that whatever you do, especially if you do CRISPR or anything like that, you have to preserve both. Now, and if you don't do both, that's when it becomes, quote, immoral. Now let's take a look about the disagreement between, say, faith-based, Christian-based, and other secular forms. I will propose to you it's all about intrinsic dignity, about whether or not that intrinsic dignity exists. So here's Ruth Macklin, dignity is a useless concept. And then here's Pinker up at Harvard, the stupidity of dignity. So what they want to affirm is not dignity, but autonomy. So the autonomy is the priceless thing. The autonomy, the freedom to decide on your own how to live your life, that should be the foundation. That's invaluable, and that should be inviolable. So instead of ethics of dignity, we are confronted, especially in the first world, with an ethics of autonomy. But now here's the question. Why is autonomy worthy of respect? Okay, so this is the view, and this is Kant. So Kant, German philosopher, Kant is coming from a Christian world. So he just assumes that the ability to choose, the ability to think, these are really cool things. But again, if you go to Asia, where I am now, in India, cows are more valuable than humans. So what ends up, a cow can shut down an entire expressway just by being there. What happens now is it relativizes the human person. Like, why is it that human beings are valuable? So intellect and will, you need both in order to be autonomous. They're evolutionary adaptations. That's a Course 7 statement, okay? They're not intrinsically more valuable than other adaptations. This is a Darwinian claim. And in order to see this, I just want to ask you this question. If you found yourself in the polar tundra, would you choose to be an autonomous human being or something else? Now, this is John Rawls. So John Rawls has, up at Harvard, political science, he had a veil of ignorance. If you went behind that veil, you didn't know what role or position you played in society. And so you had to come up with a set of rules to govern a liberal society. I'm just saying, it's the veil of ignorance. It's the veil of species ignorance. So you go behind that veil. You have no idea what you're going to be when you show up. All you know, you're going to be in the tundra. Are you always going to be a human being? I don't think so. Because being a polar bear is more valuable than being a human being in the Arctic tundra. Now, it's interesting. It suggests that value of organism is niche dependent. It's where you are. If you want to be an organism in Cambridge, Mass, you better not be a polar bear because you'll be dead polar bear. They're going to shoot you on the street because you're a threat, right? But if you are here, you want to be a human being. On the Arctic tundra, you don't want to be a naked human being. You just freeze up. You want to be a polar bear. So you see, it relativizes absolutely everything. So then there's no reason to believe that being autonomous is valuable intrinsically, that we have to protect it at any cost. Do you see? So what actually happens now is it's not intrinsically more valuable. Now, in contrast to autonomy, look at dignity. So if you look at dignity, dignity grounds all equality. And I said this is a conversation I've found myself in Asia now, especially women and men. The view that women are not as equal is very shocking, because I've been formed in the global north. And when you counter that, you go, women are not equal. They should be subservient to men. And they will argue, they will make arguments based on biology. They will make arguments made on strength. And it's interesting, I discovered men were always more powerful than women until the discovery of the gun. Because in close contact, the man always had physical advantage. Now you can just shoot him from afar. So now you have intrinsic dignity, right? Intrinsic dignity explains why we're equal. It also explains why we are more worthwhile, more valuable than other plants or animals. We live in a society where there's a view now that we are just like all the other animals. And so, like several years ago, there was a British woman, she wanted to marry a dolphin. And she fell in love with this dolphin in Israel. I don't know if it's still alive right now, but so she wants to marry it. So she said she should be able to marry that dolphin because she's just as valuable as that dolphin. because that dolphin has dignity as well. So you see how if you lose this sense of intrinsic dignity, everything's extrinsic, everything comes from outside, everything is bestowed, then you can that dignity goes way up and down. So for an ethics of dignity, dignity is the ground for autonomy, which is why dignity concerns can limit and constrain autonomy. You see, once you realize that if you look at autonomy emerges from dignity. It is because we are worthwhile, because we have intrinsic value, that our capacities of intellect, will are special. Then you see that dignity can constrain because it is the foundation. So should we use CRISPR? The way that will be then translated is, how do we use CRISPR in humans in a way that respects their dignity? This is the way that we would formulate it. And in the closing slides, I'm just going to focus on therapeutic versus non-therapeutic. This is one distinction. Remember, preserve and promote health and well-being on one hand, and to preserve and promote personal and social autonomy on the other. And then this one, somatic gene editing to modify the genome of a present person, and this germline gene editing to modify the genome of a future person. And then you have a matrix, then you have a grid. So this is the ethical grid. So you have therapeutic and non-therapeutic with somatic and germline gene editing. This covers pretty much the entire landscape of what CRISPR can be done for humans. And I'm proposing the following ethical constraints. So therapeutic, somatic gene editing, yes. I'll explain why. And then germline gene editing, no. I will explain why that case. And I will also indicate a no maybe here. And I'll explain why there in a minute. So why yes? So if we use somatic gene editing as a therapy, it's safe and effective, then we should use it just like we use every other medical tool or intervention to alleviate suffering, to cure disease, and to protect health and well-being. I mean, that's just as long as it's safe and effective, right? Now, we're going to talk about affordable, especially now that I live in the Philippines. CRISPR is just far beyond reach. I mean, we're dealing with CRISPR in yeast. We're not dealing with CRISPR in people yet. Now, with regards to germline gene editing, and the no is actually for both, what I'm proposing is the following. We have limitations on therapy on human beings based on informed consent. If you went to the hospital today and the doctor wanted to cut you open, the doctor wouldn't be able to cut you open until you gave consent. And one of the things you must know before you can give consent is the benefits and the risks of the surgery. And they'll tell you that. You have stage 2 cancer. If we do this surgery, we'll remove it. You could be cured, but the risk is pain. They always end up with death, right? So there's always, they'll give you all the risks. Now, here's the thing. And if they didn't do that, it would be unethical because you would not be able to give consent. You could give consent, but it's not informed because you have to know why you give consent. Now, here's the problem. For germline gene editing, we would not know the benefits and the risks without actually doing experiments on future persons. Because you can only take animal experiments so far. If you look at COVID, we took it all the way to chimps, and then we had to do some of the largest clinical trials for a vaccine ever. And they were from all over the world. Now, it's interesting, in the Philippines, they will say, well, they were done with whites. Were they done with Asians? And so they tried very hard to have a demographically diverse population set in order to see the effects on different populations. Now, you see, we won't be able to do that with CRISPR because you can't you can't know the risks and benefits unless you have a human patient. You need a clinical trial. You have to sign off. Well, the future person, the little offspring, the little baby who doesn't exist yet, can't do that. So what actually happens is that this, in principle, is an ethical block forever. Because you cannot do the experiments on the CRISPR babies without risking their health and their lives without their consent. Now, there's a whole debate about whether or not parents can consent to that. The challenge is that often, and I have to, walk with people who are struggling with infertility, and it's an incredible cross, incredibly painful. But the danger there is that you are trying to fulfill their needs and their desires at the expense of the health and well-being of their children. Okay? So I've basically said, no, you couldn't do that. It would be no for both. For the non-therapeutic, other issues, so the questions of social stigmatization, discrimination, social pressures will pressure parents to design their children. And I was giving a talk in New York, and I pointed out that in New York, when you're pregnant, you already sign up the kid to the kindergarten, because the kindergarten you go to kindergarten. If you go to this kindergarten, you go to that grade school, you go to that grade school, you go to high school, and you end up at MIT. So the kid's just in utero, and he's already in a line. He's already on the list. The parents have already listed him on this elite kindergarten in Manhattan. So now, let's just say the parents have access to gene editing. So let's just make our kid, I don't know, X, Y, or Z, right? And there's genetically edited children. So when I bring this up with high school students, they will always say this. I say, well, wait, let's say you found out today that you're genetically edited. You know what they'll say to me? They'll say, I wonder if my parents would have loved me the way I should have been. It's an interesting psychological existential question. Do you understand? The view that someone designed you, that you are the product of someone's imagination, you want to be not that. You want to be you. See, the human person wants to be unique and independent. And the fact that you are designed. Now, I point out that one of the things, if you ask people, you have polls like, what would you want your kid to be? They all want their kid to be tall. And there are a lot of social experiments that show that, we elect taller people over shorter people. But if they're about the same, we tend to pick the taller people. Taller people have inherent social advantage in society. It just is. Now, I point out, too, that taller people have significant disadvantage, too. Look at the plane. Basic economy doesn't work for tall people anymore. They have to go at least for, not premium economy, like extra comfort plus or whatever it is in the front. Because I've seen them. They're like, now, it might be great for an hour, but if you're going to the Philippines, like I'm flying tomorrow, it's 14 hours from New York to Narita. Your length is a major disadvantage on that plane. There could be major plane rage there. So what you see here is that for many reasons, I've ruled out non-therapeutic. There's a maybe for the following thing. It came up at a talk I was giving a year or so ago. Are there possibilities where you could imagine that our society would non-therapeutic gene editing for the sake of the common good? And so the example that we worked out in this talk is the following. You have someone who's basically a lifelong FAA, air traffic controller, and you want to give them better than 20/20 vision. You have a genetically engineered tool that you can inject in the eye. It makes their eyes just so much better, $6 billion eyes. And they get to see the planes. They get to see the planes in fog. Do you understand? So the idea is, are there scenarios where our society would be okay with, and this is something we can discuss, okay with certain non-therapeutic enhancement type genetic changes that would benefit not you individually. Now, it could, of course, but given your lifelong vocation, profession, would help all of us. So that's a maybe, because I'm not sure yet, actually. I'm not sure, because I think that after that, the FAA air traffic controller is going to quit and go do something else and use those super eyes to do something he can do for a lot more pay that other people who don't have super eyes can do, right? So how are you going to limit that? All right, so this is my last slide. So for ethics, the somatic cell modifications, I believe, can be morally justified, have to be safe, therapeutic, effective, et cetera, For present persons, for future persons, I'm ethically opposed, because I do not think we will be able to do the kind of proper ethical analysis that needs to be done in order for us as a society of dignified human beings to treat each other with the value that we have. So thank you very much for your kind attention.
Thanks for listening to this lecture on the Thomistic Institute podcast. The generosity of people like you makes this podcast possible. If you enjoy these talks, please consider showing your support at www.thomisticinstitute.org/donate. Your donation of even $1 helps us reach more college students and many others with the powerful truths of the faith, and it ensures that we can keep publishing top-notch lectures on this podcast. Thanks a lot.